Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today we're talking 9.3, how to find the trigonometric functions of any angle, as well as how to use that to find points around a circle. So, first things first, I want to give you a sample problem for us to take a look at and solve. Say, for a moment, I give you the following. I give you a circle. And I also give you a couple extra pieces of information. First of all, this circle is supposed to be centered at the vertex. I'm just a really bad artist. And second off, this circle has a point. This point is at 3, 4. Could you use these two pieces of information to find the radius of the circle? Well, at first it seems pretty easy, like, yeah, it's out this far, but how far is this far? Well, we can use a couple bits of knowledge from 9.1 to help us out. It all starts with visualizing what we could do with this radius. We could turn this radius into the hypotenuse of a right triangle. So what if we brought the sides like this? We had a right triangle here. Well, then surely we could start to figure out what r is. All we would need are either the angle, which we don't have, or the side lengths, which, hang on a second, we might be able to figure out here. If our x value is 3, that means this dot is 3 to the right. So the length of this segment is 3. And if the y value is 4, that means that this is 4 units up. So here's 4. Using these pieces of information, now can we find r? Sure we can. We can use the Pythagorean theorem. We know that 3 squared plus 4 squared equals r squared. 3 squared is 9, 4 squared is 16. So 25 equals r squared. And we just found our radius. Our radius is 5. Done. The idea of having a point and a radius is very, very powerful. Even more powerful if we know an angle. So let's take a look at this page right here. You can generalize the right triangle definitions of trigonometric functions so they apply to any angle. This is referring to the fact that all the way back in 9.1, we had a table that helped us learn about what happens at 30 degrees, 45 degrees, and 60 degrees. But the general definition is this. Let xy be a point where the terminal side of this angle intersects the circle with radius r. If this is the case, we can actually figure out what the different sides are based on the different trigonometric functions. So here we are told that sine of theta, again, we don't know what theta is, but it works for any angle. The sine of that angle theta is equal to y, the height here, divided by the radius, r. The sine is defined as y divided by r, and it doesn't matter what y is, this will always work. This is because normally, when we're talking about sine, we're talking about the opposite over the hypotenuse. In this case, our hypotenuse is r, and our opposite side is this one. So this works for any angle, for any point. These functions are sometimes called circular functions, I should mention. Another circular function is the cosine of theta. So with the cosine of theta, it's usually adjacent over hypotenuse, but here our adjacent side is just x units long. So it's x over the radius. Tangent is a little bit difficult because tangent is usually opposite over adjacent. That's y, the y value of the point, divided by the x value of the point. This works out great in most cases. In most cases, you can literally just divide the y by the x, and you've got the tangent. But if your x is 0, meaning that you are somewhere in the middle, your tangent is not going to work out because you can't divide by 0. You get something undefined. And of course, our reciprocal functions are also there. Cosecant, secant, and cotangent. Let's see if we can use this to help us. So in example 1, we're trying to figure out the 6 trigonometric functions of this angle, theta. Again, it doesn't matter that theta isn't in between the parts of this triangle now. We're talking about any angle theta that creates a radius r. So it goes to say that we can find the sine, cosine, and tangent, and then flip them to find the cosecant, secant, and cotangent. Whoops, I didn't mean to put cotangent there. I was saying cotangent, it went down on the paper. But this should just be a tangent of theta. Cool. Well, the first thing we need here is to recognize that sine of theta, according to our notes, is the y value of the point divided by the radius. We have a problem here. We know the y value is 3, but we do not know the radius. There's a reason why I gave you this warm-up, y'all. We can find the radius if we know this point, because that point represents this side, it's 4 long, and this side that's 3 high. You can solve for the radius using the Pythagorean theorem. A squared plus b squared equals c squared. When we do this, we get that 3 squared plus 4 squared equals r squared, which is 9 plus 16 equals r squared, which, hey, this one's just like the warm-up we did. 25 equals r squared, so we square root both sides. 5 is our radius. That's our missing sine. So if sine of theta is y over radius, then sine of this mysterious angle is 3/5. What about the cosine? Well, cosine is just the x of our point divided by the radius. The reason why this works, again, is because cosine is adjacent over hypotenuse. The adjacent side is 4, the hypotenuse is 5. So it's 4/5. And for the tangent, we don't even need to know the radius, because the tangent is just y divided by x. Our y is 3, our x is -4. Oops, sorry, y'all. This should be, negative 4/5. I realized I forgot the negative there. So, all we need to do is just do y over x. That's 3 over -4. Done. Now, of course, we can also find the reciprocals. The cosecant of theta is just flipped from sine. That's 5/3. The secant of theta is just -5/4. And the cotangent is -4/3. Done. No sweat. This is a very powerful tool, so remember these little ideas. If you remember your SOHCAHTOA, you can figure this out as well, but if you remember it, it comes a little quicker. Let's flip the page. On the next page, it talks about something called the unit circle. The unit circle is a circle that has a radius of 1. That's why it's called the unit circle. The reason why the unit circle is so important is because if our radius is 1, then our sine and cosine become super easy to find. Our sine and cosine turns into just y over 1, which is just y, or x over 1, which is x. That means if you know the coordinates of the point, you know what the sine and cosine are. It's like a quick shortcut. We've actually talked about the unit circle once before in our last notes as well. We use that to help us find the different angles and the radians that correspond with them. So here's what I want us to do. I want us to take out that unit circle worksheet if you have it, and if not, I'd like you to take a minute to copy it down on a separate sheet of paper. Unfortunately, my camera doesn't reach high enough to show the whole thing, so we'll do it in bits and pieces. So, here is the unit circle in most of its glory. Oh, I can just barely fit it. There we go. Take a second and copy this down if you haven't already from last lesson. Pause the video and try it out. Hopefully you've had a chance to copy all of this down. What we are going to do now is we are going to interpret this as follows. The radius of this circle is 1. It's a unit circle. So if this is our origin, this is the middle of our circle, and we're going 1 away, what are the coordinates of a 0-degree angle, or a 0-radian angle? Well, its x value is 1, its y value is 0, so we can fill in 1, 0 for the coordinates. Okay, let's go over to 90 degrees. If we're just going straight up on our y-axis, well, the x value is 0, but the y value is 1. Okay, that's kind of nice. I think we're starting to see a pattern here. What if I go 1 unit to the left, 1 radius to the left? Well, then our x value is -1 and our y value is 0. And what if we go straight down? Well, straight down, that's going to be an x value of 0 and a y value of -1. These 4 almost goalposts in our unit circle are very important because they will help us keep track of where we are and how far away we have to go. In fact, these 4 coordinates with these nice numbers are so important that they actually have their own name. These are called quadrantal angles. Quadrantal. It's based off of the word quadrant. If you remember your quadrants from middle school, you'll recall that quadrant 1 is where your x and y are positive. Quadrant 2 are where your x is negative but your y is positive. Quadrant 3 is where both your x and y are negative. And quadrant 4, this last one over here, is where you have a positive x value but a negative y value. 1, 2, 3, 4 quadrants. What I'd like us to do is to consider the fact that in these quadrants, there are certain things that are always going to be positive and some things that are always going to be negative. In quadrant 1, x and y are positive. In quadrant 2, our y is positive, but our x is negative. In quadrant 3, they're both negative. And in quadrant 4, we have our x is positive and our y is negative. This is going to come in handy a little bit later. But we've got our quadrantal angles. Let's see if we can find a measure of a quadrantal angle. So we're asked to use the unit circle to evaluate the following functions. We're trying to evaluate the sine of 270, the cosine of 270, the tangent of 270, the cosecant of 270, the secant of 270, and the cotangent of 270. Cool! Let's use that same trick we learned from last time. Unfortunately, we've got a bit of an issue here. Sine is usually going to be y over the radius. But what's our radius? It's just 1. So our y value then is all that's left over. What's the y value of the point at 270? Well, 270, we said that was straight down 1, so it's at -1. The sine of 270 degrees then is -1 over 1, which is just -1. The cosine is also going to be pretty easy, but it has that little caveat that r is 1. So it's just going to be your x value. Since it's x over r, and our radius is 1, we'll just say that it's x. What's our x value? Well, that's like 0 over 1, or just 0. Again, I sort of flipped back and forth here. You could write it as 0 over 1, but no matter what, you're going to get 0 at the end. The tangent is where it gets funky, and not in a cha-cha slide kind of way. Tangent is always going to be y over x, or opposite over adjacent. But here, both our y and x are numbers. The y value of this point was -1, the x was 0, so we end up with -1 over 0. Well, wait a second. We can't divide anything by 0. We would say that the tangent of 270 degrees is undefined. There we go. It's undefined. Now all we need to do for the cosecant, secant, and cotangent is to flip them. So for the cosecant, it was the sine was -1 over 1. That's just 1 over -1, which, hey, wait a second, that's just the same number. It's -1. The cosine was 0 over 1, so the secant is 1 over 0, but we discussed what happens when you divide by 0. We get an undefined function. It's undefined. The cotangent is nice because what was originally -1 over 0 is now 0 over -1. 0 divided by anything is just 0. Very, very nice. We are now going to diverge a little bit from what we have just learned in the notes to go back to this unit circle for a minute. Because this is not the only part of a unit circle that's useful. You see that in all these other parts of our unit circle, we have these points that we need to fill in. These points, if you can memorize a way of basically figuring them out, will help you always find the sine, or the cosine, or the tangent of just about anything with these angle measures. So, let's see how we do it, and then we'll actually go ahead and do it, and create these measures. Let's start off with our 30-degree angle. So our 30-degree angle looks like this. I'm going to make a smaller unit circle just on the back side here, just so we can demonstrate at least. Here's our unit circle. Goes all the way around. It's a pretty bad circle, but whatever. If we were trying to figure out the coordinates of the point at 30 degrees, but we know our hypotenuse is 1, we could set up trigonometric ratios to solve for them. Let's start off by figuring out what this opposite side is. Actually, yeah, let's do it. Let's figure out what the height of this opposite side is. Well, we know that if we're talking about an opposite, which we're going to call y, because that's how high up we'll be, and we know our hypotenuse, the sine of 30 degrees equals y over 1. So we should figure out what the sine of 30 degrees is using our calculator. You can also use other tricks to get you here, but for the purposes of today, I'm just going to type in sine of 30. It's 0.5. So the y value of our point here, right here, is 0.5, but I'm going to write it as 1/2 for reasons you'll see later. This is 1/2. Now, we could figure out the x value a similar way by taking the cosine, but I'm going to let you know you're going to get a nasty, nasty decimal. Instead of doing that, I want us to see if we can use the Pythagorean theorem to solve for x, which is the length of this triangle. Let's do it. Let's find the x of this point. A squared plus b squared equals c squared. C squared is just our hypotenuse of 1. So it's really x squared plus 1/2 squared equals 1 squared. Well, this just simplifies to x squared plus 1/4 equals 1. Now we just have to solve for x. We can subtract 1/4 from both sides, getting x squared equals 3/4. And from here, to solve for x, don't we just have to square root both sides? X equals, anytime you take the square root of a fraction, do the square root of the top, so square root of 3, divided by the square root of the bottom, which is just 2. X equals root 3 over 2. That is the coordinate point here. Which means, if you were ever asked what the sine of 30 degrees is, it's 1/2. If you were asked what the cosine of 30 degrees is, it's root 3 over 2. Done. No need to fuss around with it. Now, instead of us repeating this experiment with these other points, which we absolutely could, and we'll get these weird numbers, I want to instead show you a bit of a trick to memorize them. Because like I said, these are very useful if you know them. It's called the left hand rule. What I'd like you to do is I'd like you to take your left hand and lay it out across these points. And you'll notice that each finger corresponds with a different line. Our pinky here is where 0 is. Our thumb here is where 90 degrees is. And our 3 fingers can represent the other missing angles. In fact, let me pause here for just a moment so I can label my hand and we can see it live. Here we are. This is the left hand, and these are all the angles that correspond with it. You don't need to write this on your left hand, obviously. I'm trying to show you a trick to make this quicker. To quickly figure out the x and y values of the point, or to figure out the sine and cosine, all you need to do is lower the finger in question and compare how many fingers you have on top to how many fingers you have on bottom. The number of fingers you have on top is going to be your x value, or your cosine. It's going to be the square root of this number of fingers, in this case 3, divided by 2. So, if you wanted to figure out the cosine of 30 degrees, or the x-coordinate of the point at 30 degrees, you would say that it's square root of 3 over 2. To figure out the sine, or the y value, you look at the number of fingers below the one you put down. So if I have one finger below the one I put down, it's the square root of 1 over 2, which is just 1/2. That's our sine, or our y value of the point. And this works for anything in this quadrant 1. If I put down my middle finger to figure out 45, let's take a look. I've got 2 fingers above, so my cosine, or my x value, is the square root of 2 over 2. It's always going to be divided by 2 here. What would the y value, or the sine, be? Well, I've got 2 fingers below the one I put down, so that's going to be square root of 2 over 2 as well. And that makes sense because this is a point that's directly up and over by the same amount. Last but not least, we can do it with 60 degrees. How many fingers are above? Just the 1. So that's the square root of 1 over 2, which is just 1/2. I'm actually just going to write that down as 1/2. You can see that that's 1/2, right? 1/2 over, again, here we have 3 fingers below, so it's the square root of 3 over 2. This is a great trick to help you know what's what. But Mr. Strager, I hear you say, does this rule work for the other quadrants? Kind of. It kind of helps us for the other quadrants as well, but we'll need to adapt our left hand. Now I'm half wishing I didn't write down all these numbers. For this one, if you want to use the left hand rule, just keep in mind that all of your x values are going to be negative and all of your y values are going to be positive. Also keep in mind that we're basically just rotating our left hand 90 degrees to this direction. So we would treat them the same way as the previous terms. However, we would treat the x value now as being where our pinky is, whatever's above, and the y value as being whatever's below. So for instance, if I wanted to find the 120 degree angle, I put down this pinky, or this ring finger I should say, there's 1 above, so the x value is going to be 1/2. There's 3 below, so it's going to be square root of 3 over 2. But just remember that this would not be correct. This would be the exact same as 60 degrees. In quadrant 2, our x values are negative, so it's negative 1/2, comma square root of 3 over 2. 135 degrees is going to be the same as 45, just with a negative x value. So it's negative root 2 over 2, and then positive root 2 over 2. 150 degrees is the same as 30 degrees, so the x is negative root 3 over 2, positive 1/2. We have just used our left hand to fill out all the coordinates of every point around the top half of the unit circle. Now it is up to you to fill out the bottom half. Before you do so, I will give you a little bit of a hint. These top numbers, we were able to figure out quadrant 2 by just flipping all these, making the x value negative. If we flipped these points, could we figure out the points down below? Pause here and try to see if you can fill in the rest of the coordinates for the unit circle. I'll be back in a couple of seconds here. But pause and see if you can do it. Let's fill in the rest of this table. So, if we go directly down from here, it looks like it's going to be the same as 150 degrees. It's going to be negative 3 over 2 for the x value, and for the y value, it's going to be negative 1/2, because we flipped it over the x-axis. So all these values are going to be negative. This is going to be negative root 2 over 2, and negative root 2 over 2. This one's going to be negative 1/2, comma negative root 3 over 2. Over here, our x's are positive, so it's like we're flipping these upside down, but the y's are negative. So if 60 degrees was 1/2 root 3 over 2, 300 degrees is positive 1/2 negative root 3 over 2. So that means that this next one here is going to be, for 7 pi over 4 radians, or 315 degrees, root 2 over 2, negative root 2 over 2. And for the last one, root 3 over 2, negative 1/2. We have just filled in our entire unit circle at this point. And we can use this as a resource to help us with any future calculations. The unit circle is so useful as a tool. It can't help us in every situation. If I give you a weird angle like, I don't know, 36 degrees, we're sort of stuck. But we can use it in most situations. We're going to come back to using the unit circle in a second. But for now, I'd like us to talk about something called a reference angle. So let's say that theta is just any angle in standard position. The reference angle in this case, which is very aptly named, is the acute angle formed by the terminal side of theta and the x-axis. We've already used reference angles without even knowing it to help us make angles, to know where to draw them. The relationship between these is that we end up with essentially almost supplementary angles in most cases. Here's the deal. If you have an angle that's in quadrant 2, all you need to do is ask yourself, what do I need to add to my angle to get to 180? That's your reference angle. It's whatever you need to add. If you're in quadrant 3, it means you've gone a little bit past 180, right? So just subtract 180 from your angle, and you've got the part of the angle that's past 180. And for quadrant 4, we're almost a full circle around. We're almost at 360. We just need to subtract our angle to get our reference angle, how far away it is from the end. We can also do the same thing with radians. With radians, it's even simpler, because with radians, it's just, in quadrant 2, pi minus theta. In quadrant 3, the reference angle is theta minus pi. And in quadrant 4, it's 2 pi minus theta. So let's see if we can do this. We're trying to find the reference angle for 5 pi over 3. Our first question we should ask is, where is 5 pi over 3? Is that quadrant 1, 2, 3, or 4? And guess what? We've got a tool that can help us. 5 pi over 3 is right here, soundly in quadrant 4. That's 300-degree angle. So we know that if we wanted to find the reference angle for quadrant 4, theta prime is what this is called, is equal to 2 pi minus 5 pi over 3. If you wanted to convert this into a fraction so you can subtract them, I would recommend it. 2 pi is the same as 6 pi over 3. So what's 6 pi over 3 minus 5 pi over 3? It's pi over 3 radians. The reference angle to 5 pi over 3 radians is pi over 3 radians, because that's what makes it 2 pi. For part B, we have a negative 130-degree angle. So we're going 130 degrees backwards. It might help you to think of this, instead of as a negative 130-degree angle, to think of what's coterminal to it. So remember, to find a coterminal angle, you can add or subtract multiples of 360. We want to add 360 here so we can get a positive coterminal angle. This is going to give us 230. This is the same as a 230-degree angle. So, if we look on our chart, 230 degrees is in between 225 and 240. So it's in quadrant 3. The rule for quadrant 3 is theta prime is equal to our angle measure, which in this case was 230, minus 180. In other words, we're asking, how far past 180 do we have to go to get to 230? And that's just 50 degrees. Our reference angle is a 50-degree angle from the x-axis. Done. Let's flip the page to the very last page of 9.3. And this, oh boy, this is where the unit circle is going to come in handy. I'm going to show you how to solve these problems the way the book is solving them, and then I'm going to show you the way to solve them using the unit circle. You can use whatever way you prefer, using reference angles or the unit circle. But just know that if your unit circle is asking for the sine, or the cosine, or the cosecant, or the secant, it's probably going to be quicker to use the unit circle, because you know it's just going to be the x or the y value, or the reciprocal of the x or y value. Let's start by using reference angles to evaluate the following functions. Before we jump into it, the steps they give us here are very helpful. The steps for this are, find a reference angle, evaluate the trigonometric function for that reference angle, then determine the sign based on the quadrant. The notes give us this. It tells you exactly what functions are positive or negative in what quadrants. If you just remember that your x values are positive or negative in certain quadrants, you don't need this table. Let's take a look and see if we can do the tangent of negative 240 degrees. Again, we've got this negative angle. So first things first, negative 240 degrees is coterminal with what? Well, if we add 360, we get 120 degrees. So let's actually do the math based on a 120 degree angle. It'll be a little bit neater to do. Okay. So what's the reference angle to 120 degrees? We know 120 is bigger than 90, but it's less than 180, so it's in quadrant 2. The reference angle for something in quadrant 2 is to do 180 minus that angle. 180 minus 120 equals 60 degrees. So our reference angle is 60 degrees. What we would need to do from here is to figure out what the tangent of 60 is. Just keep in mind that it's negative because our tangent is negative in this quadrant. If you weren't sure about it, just remember, tangent is opposite over adjacent. In this case, our adjacent, our x value, would be negative. So we know that the tangent of negative 240 degrees is the same as the negative tangent of 60 degrees. Again, it's negative because it's in quadrant 2. So what's the tangent of 60 degrees? Well, from here, we would need to actually have to figure out, basically, what the tangent of 60 degrees is. You could do it using your calculator, or you could do it using your building a triangle. Up to you, ultimately. Either way, we get the square root of 3 is the tangent of 60 degrees. Mr. Strager, how did you get square root of 3? Well, there are a couple of ways, like I mentioned. The table in our notes for 9.1 could help us here. We could use this table of values, so you don't have to memorize, to find that the tangent of 60 degrees is square root of 3. Or we could use our unit circle. According to our unit circle, a 120 degree angle. If we were trying to figure this out, this would be the square root of 3 over 2 divided by the negative 1/2. It's y over x. So using the unit circle method, we would say that the tangent of negative 240 degrees is just the same as the tangent of either a 120 degree angle or negative tangent of 60 degrees, however you want to put it. It's going to be our y value, which is the square root of 3 over 2, divided by our x value, which is negative 1/2. I don't like dividing fractions this way. We end up with a totem pole. So why don't we treat this as keep, change, flip territory? We keep root 3 over 2, we change division to multiplication, and we flip this to become negative 2 over 1. The 2's cancel out, and we get negative square root of 3. Done. That's how we can use the unit circle. So with the cosecant of 17 pi over 6, remember, cosecant is the opposite of sine. I'd like you to pause the video and pick which method you would like to do. Do you want to figure out where 17 pi over 6 is on the unit circle and figure out what the sine would represent? Or do you want to use the reference angles? Either way, pause the video and I will show you the steps in just a little bit. So everybody, let's first try and figure out what's coterminal with 17 pi over 6, because 17 pi over 6 is huge. Well, to figure out what's coterminal, we can subtract multiples of 360 degrees, or 2 pi. So what's 17 pi over 6 minus 2 pi? Well, 2 pi is the same as 12 pi over 6. So let's just 5 pi over 6. That's the radians that we're doing. So 5 pi over 6 is really what we're trying to figure out the cosecant of. Recall that cosecant on a unit circle, I'm going to be using the unit circle to help us with this, the cosecant of 5 pi over 6, it isn't opposite over hypotenuse. In other words, it isn't our y value over 1, it's the reciprocal. It's 1 over the y value. So we can use our unit circle to reference what's the y value at 5 pi over 6. Well, if I look at my table, 5 pi over 6, or 150 degrees, the y value is 1/2. So what's the reciprocal of 1/2? It's just 2. The cosecant of 17 pi over 6 is the same as the cosecant of 5 pi over 6, which is just 2. Done. For example 5, we're going to try and solve a real-life problem. And I want to preface this by saying, you do not need to know this formula. This is a specific formula for this specific problem. But it is a good formula. It's actually the distance traveled in feet by a projectile given an initial speed and your initial angle. So we're talking golf here. We're hitting a golf ball at a 50-degree angle with an initial speed of 105 feet per second. All we need to do to figure this out is we just need to plug it in. So, if we do d equals, our velocity in this one is 105 feet per second, so it's 105 squared over 32 times the sine of 2 times theta. If theta is 50 degrees, 2 times theta is 100 degrees. So it's the sine of 100. I hate this example after just talking about the unit circle, because unfortunately the sine of 100 degrees is not a nice number. It isn't. It's a crazy decimal. But we can still evaluate this. To evaluate this problem, all we need to do is plug it into our calculator. So we should do 105 squared. Actually, let me put this into a fraction so it looks like the one that we see here. 105 squared divided by 32 times the sine of 100 equals this. That's our distance. The distance the golf ball travels is about 339.30 feet. That's a little bit anticlimactic for all that we've done so far, but it's how you would solve a real-life problem like this. Plug in and evaluate. Let's say for a second that I change this up slightly. Let's say, what if theta was actually 60 degrees? We can actually get an exact number here because of this. If theta was 60 degrees, d would equal 105 squared divided by 32 times the sine of 2 times 60 is 120 degrees. And hey, we know from our unit circle the sine of 120 degrees is just going to be a perfect number. If I look on my unit circle, the sine of 120 degrees is the y value, at 120 degrees. The y value at 120 degrees is root 3 over 2. So d, the distance, is just 105 squared over 32 times root 3 over 2. We can go ahead and simplify this fraction as much as possible to get an exact answer. So, first off, 105 squared over 32, if I want to simplify it using my calculator, just put it into a fraction form like this, it'll straight up simplify it for you. What we get is that d is 11,025 over 32 times root 3 over 2. We can then combine these two fractions to get an exact distance answer with no decimals needed. It's 1125 root 3 over 64. That's how many feet it travels. And just to check to see if 11,025 over 64 simplifies, it doesn't. So this is our final answer. How vastly different these approaches are. Either way, everybody, that concludes our notes for 9.3. Thank you so much, and I hope you have a fantastic rest of your day.